This advanced Python course covers essential professional-level topics, starting with advanced object-oriented programming concepts like multiple inheritance, polymorphism, abstract base classes, and property decorators. It then delves into decorators, generators, iterators, and iterables. Core libraries such as datetime, math, random, OS, sys, JSON, and pickle are introduced, along with regular expressions and working with files and APIs. The course teaches testing using unit test and PyTest, debugging with PDB, and logging. It also covers concurrency with threading, multiprocessing, and async programming using Asyncio. Database interaction is taught using SQLite 3 and SQLAlchemy. Lastly, it explores GUI development with Tkinter, PyQt, and Kivy. By the end, learners will be ready to build professional Python applications across various domains.
Advanced OOP concepts. Multiple inheritance.
In Python, multiple inheritance means that a class can inherit from more than one parent class. This allows the child class to reuse and extend behavior from all its parents. However, when two or more parent classes have methods with the same name, Python needs a way to resolve which one to use. That's where method resolution order, or MRO, comes in. MRO defines the order in which Python looks through classes to find methods. We use the built-in super function to help Python follow this order correctly and to reduce ambiguity when calling methods from multiple parents. Let's look at an example. Here we define two parent classes, Class A and Class B. Each class defines a method named speak. Then we define Class C that inherits from both A and B. When we create an object of Class C and call the speak method, Python uses the method resolution order to decide which method to run. Since Class A appears first in the inheritance list, the method from Class A is called. We can print the MRO by using the built-in attribute c.__MRO__. It shows the exact order Python uses to search for methods. In this example, Class B inherits from Class A and overrides the speak method. Inside B's version of speak, we call super.speak, which goes up to Class A. Class C then inherits from B and also overrides speak, calling super.speak again. When we call the speak method on an object of Class C, each method in the chain is executed in order, from Class A to Class C. This demonstrates how super allows all classes in the inheritance hierarchy to participate, following the MRO properly.
Polymorphism.
Polymorphism in Python means that a single method name can behave differently depending on the object that calls it. This is often used in class hierarchies where different subclasses override the same method from a base class. It allows us to write code that works with objects of different types, yet behaves correctly for each type. This improves flexibility and reusability of the code. Let's look at a simple example using animals that speak differently. First, we define a base class named animal with a method called speak. Then we create two subclasses, dog and cat, that override the speak method to provide their own behavior. We define a function named makeItSpeak that accepts an animal object and calls its speak method. When we pass a dog, it barks. When we pass a cat, it meows. This is polymorphism. The same method call results in different behavior depending on the object.
Abstract base classes, ABC.
Abstract base classes, often shortened to ABC, are used in Python to define method signatures that must be implemented by any subclass. They act like templates, enforcing a contract for future classes. To create an abstract class, we use the built-in module named ABC, which stands for Abstract Base Classes. Inside it, we use the class ABC as a base class and decorate abstract methods with @abstractMethod. If a subclass does not implement all the required abstract methods, it cannot be instantiated. This is a powerful way to design reliable and predictable class hierarchies. Here we import ABC, an abstract method, from the ABC module. We define a class called shape that inherits from ABC. Inside it, we declare a method named area and mark it as an abstract method using the decorator @abstractMethod. Then we define a subclass called circle and implement the area method with a real formula. When we create a circle object and call the area method, it returns 78.5. But if we try to create a shape object directly, Python will raise a type error because the abstract method is not implemented in shape itself.
Properties and @property decorator.
In Python, we use the @property decorator to turn a method into an attribute-like access point. This lets us define methods that can be accessed as if they were simple attributes, but with logic behind the scenes. It's useful when we want to control access to private data or add validation without changing how the property is accessed. We can also define a setter using @property.setter and a deleter with @property.deleter. This pattern supports encapsulation while keeping the code clean and readable. Let's look at an example. We define a class called product with a private variable named _price. The method price is decorated with @property, so we can access it like a regular attribute. Then we define a setter using @price.setter, which adds a validation to prevent setting a negative price. We create a product object with an initial price of 100. We print the price and it returns 100. Then we update the price to 150 and print it again. Now it shows 150. If we try to set the price to a negative number, the setter raises a value error. This gives us full control over attribute access while maintaining a clean and simple interface.
Decorators and generators. Writing decorators.
In Python, decorators are used to modify or extend the behavior of a function without changing its actual code. A decorator is a function that takes another function as an argument and returns a new function. We apply decorators using the symbol followed by the decorator name, placed above the function definition. They are commonly used for tasks like logging, access control, performance measurement, or caching. Let's look at how to write a simple decorator step by step. We define a decorator function called my_decorator. It takes another function named func as its argument. Inside, we define a wrapper function that prints a message before and after calling the original function. The decorator then returns this wrapper. Next, we define a function called sayHello and decorate it using @my_decorator. When we call sayHello, the wrapper function is executed. It prints a message before, calls the original function, and then prints another message afterward. This shows how decorators can enhance existing functions without modifying them directly.
Parameterized decorators.
So far, we've seen simple decorators that don't accept arguments. But in real-world scenarios, we often want decorators to be flexible, for example, setting logging levels or enabling conditional behavior. To do that, we use parameterized decorators, which means passing arguments to the decorator itself. This requires an extra level of function nesting, one outer function to receive the arguments, and one inner function that acts as the actual decorator. Let's walk through an example. Here we define a function named repeat that takes a parameter n. This outer function returns a decorator. The decorator takes a function func, defines a wrapper that runs the function n times, and returns that wrapper. We then decorate the greet function using @repeat, open parenthesis, 3 close parenthesis. When we call greet, the decorator causes it to print hello 3 times. This is a great way to make our decorators dynamic and reusable with different configurations.
Using built-in decorators.
Python comes with several built-in decorators that are commonly used with class methods. The @static method decorator is used when a method does not access instance or class data. It behaves like a regular function, but is grouped with the class for organization. The @class method decorator allows a method to receive the class itself as the first argument, typically called CLS. This is useful when we want to work with class-level variables or create alternative constructors. The @property decorator is used to turn a method into a read-only attribute and can be extended with setter and deleter. Let's look at examples of all three in action. We define a class called demo with a class variable named count. In the constructor, we increment count each time a new object is created. The method greet is decorated with @static method, so it can be called directly on the class without needing an instance. The method get_instance_count is decorated with @class method, and it uses the class itself, referenced as CLS, to access the count. Finally, the status method is decorated with @property, so it can be accessed like an attribute without parentheses. We create one object, then call the class method to print the instance count. We call the static method, and it prints a greeting. Finally, we print the status property, which returns the word active.
Generator functions and yield.
Generator functions in Python allow us to produce a sequence of values one at a time, using the yield keyword. Unlike regular functions that return a value and exit, a generator pauses at each yield, saving its state. This means we can resume from where we left off, making it ideal for working with large datasets or even infinite sequences. Generators are memory efficient and often used in loops, data streams, or pipelines. Let's look at a simple example. We define a generator function named count_up_2, which accepts a maximum value. Inside the function, we use a while loop to yield numbers starting from 1 up to the maximum. Each time the function yields, it pauses and keeps its internal state. Then, we create a generator object by calling the function with the argument 3. Finally, we loop through the generator using a for loop, and it prints 1, 2, and 3. Behind the scenes, Python resumes the generator at each iteration until it's exhausted.
Generator expressions.
Generator expressions provide a compact way to write generators, similar to list comprehensions, but with parentheses instead of square brackets. They create generator objects without the need to define a full function with yield. We can use the built-in next function to manually retrieve values from a generator. When the generator runs out of values, calling next raises a stop iteration exception. This approach is useful for creating lightweight, memory-efficient iterators. Let's look at an example to understand how it works. We define a generator expression that computes the square of each number in the range from 0 to 2. This creates a generator object called squares. We call next on squares to get the first value, which is 0. Calling next again gives 1, and then 4. If we call next one more time, it raises a stop iteration exception because the generator is exhausted. This shows how generator expressions are concise and efficient, and how next can be used to retrieve values one by one.
Coroutines and send.
Coroutines are a special type of generator designed not just to produce values, but also to consume them. In a coroutine, the yield keyword pauses execution and waits for incoming data. We can send data into a coroutine using the send function. Before calling send, we must first advance the generator to the first yield using next. Coroutines are useful in event handling, pipelines, and asynchronous programming. Let's walk through a simple coroutine example. We define a coroutine function called echo. Inside it, we print coroutine started and enter an infinite loop. In each iteration, the coroutine pauses at yield and waits for a value. We create a coroutine object by calling echo, but it won't run until we call next. The first next call advances the coroutine to the first yield and prints coroutine started. Then we use send to push in the string hello, and the coroutine prints received hello. We send another string, world, and it prints received world. This demonstrates how coroutines receive values dynamically during their lifetime.
Asynchronous generators.
Asynchronous generators allow us to yield values from a coroutine, just like regular generators, but with support for asynchronous execution. They are defined using async def combined with the yield keyword. To iterate over them, we use async for inside an asynchronous function. Asynchronous generators are ideal for handling data streams, such as reading from sockets, files, or web APIs, where we don't want to block the program. Since everything runs asynchronously, we must use await or run the async function in an event loop. Let's look at an example. We define an asynchronous generator function called async_gen using async def. Inside a for loop, we pause for 1 second using await async io.sleep and then yield a value. The main function uses async for to iterate over the values produced by the asynchronous generator. Finally, we run the main coroutine using async io.run. As output, we get the numbers 0, 1, and 2, each printed 1 second apart. This shows how asynchronous generators are useful when working with data that arrives over time, without blocking other tasks.
Iterators and iterables. Custom iterators.
In Python, an object is iterable if it implements the method $iter, which returns an iterator. An iterator is an object that implements two methods, $iter and $next. The $next method should return the next value each time it's called and raise a stop iteration exception when no more values are left. This lets us define custom iteration behavior, like looping through pages in a document, rows in a table, or steps in a workflow. Let's see how to write a custom iterator class. We define a class called countdown that takes a starting number. In the constructor, we store this number in self.current. The $iter method returns the object itself, making it an iterator. The next method checks if the current value is less than or equal to 0. If so, it raises stop iteration. Otherwise, it returns the current value and subtracts 1. We create an instance of countdown starting at 3 and use a for loop to iterate through it. It prints 3, 2, and 1, then stops, just like a countdown. This is how we build custom iterators in Python.
Custom Iterables, separate iterator class.
Sometimes it's useful to separate the iterable from the iterator itself. In this pattern, the main class implements dunder iter, which returns a separate iterator object. The iterator class implements both dunder iter and dunder next. This approach is useful when multiple iterations need to run independently, or when we want to keep the data and iteration logic cleanly separated. Let's walk through a simple example. We define a class called rangeIterable that takes a start and end value. Its dunder iter method returns a new instance of rangeIterator, passing in the same start and end values. The rangeIterator class defines the actual iteration behavior. Its dunder next method returns the current value and increments it until it reaches the end. Once it reaches or passes the end, it raises stop iteration. This design cleanly separates the data holder, which is the iterable, from the iteration logic. We create a rangeIterable object from 1 to 4 and loop through it. It prints 1, 2, and 3. Each loop creates a fresh iterator, so we can reiterate if needed.
Working with libraries. Datetime, math, random.
Python includes powerful standard libraries for common tasks like handling dates, performing math operations, and generating random data. The datetime module lets us get the current date and time, calculate differences, and format timestamps. The math module provides functions like square root, constants like pi, and utilities like floor. The random module allows us to generate random numbers, select random items, and simulate randomness, useful in games or testing. Let's see a few quick examples of each. First, we import the modules datetime, math, and random. We get the current date and time using datetime.datetime.now and print it. From the math module, we print the square root of 16 using math.sqrt and the value of pi using math.pi. From the random module, we generate a floating point number between 0 and 1 using random.random. We generate a random integer between 1 and 10 using random.randint, and randomly select an item from a list using random.choice. These built-in libraries are very handy and require no extra installation.
OS, sys, util.
Python provides built-in libraries to interact with the operating system and perform file operations. The OS module helps you work with directories, paths, and environment variables. The sys module gives access to system-specific parameters, like command line arguments or exiting the script. And util, or shutil, allows high-level file operations like copying, moving, or deleting entire directories. These are very useful in scripting, automation, and deployment. Let's go through a few examples. We import OS, sys, and util. Using os.getCwd, we print the current working directory. Then we list all files and folders using os.listdir. From the sys module, we access sys.argv, which shows the command line arguments passed to the script. You could also call sys.exit to end the script, but that line is commented out for now. Using util, we can copy files with util.copy or delete folders with util.rmtree.
JSON, pickle.
The JSON and pickle modules are used for data serialization, which means saving Python objects to a file or sending them over a network. The JSON module works with text-based, human-readable data and is widely supported across languages. On the other hand, pickle saves data in binary format and supports any Python object, but it's Python-specific. Use JSON when you need portability, and pickle when you need to save complex Python objects like classes or functions. Let's see an example of how to use both. We define a dictionary with some simple data. First, we use JSON.dumps to convert it into a JSON-formatted string and print it. Then we use JSON.loads to convert it back into a Python dictionary. Next, we use pickle.dumps to serialize the same dictionary into a binary format. We print the raw bytes and then use pickle.loads to deserialize it back to the original Python object. This shows how both JSON and pickle can be used to save and load data, with the key difference being that JSON is readable and portable, while pickle is powerful but Python only.
Regular expressions. RE module.
Python supports regular expressions through the built-in RE module. We use it to search, match, or extract patterns from text using functions like search, match, and findAll. Patterns use special syntax like \d for digits, \w for word characters, and the dot character to match any single character. It's important to write patterns as raw strings using a lowercase r before the quotes. For example, r quote \d plus quote. Let's look at a basic example that shows how these tools work. We import the RE module and define a string containing a name and an ID. First, we use re.search with the pattern \d plus, meaning one or more digits, and find the first number. Calling group on the match object gives us the value, which is 123. Next, we use re.findAll with \w plus, which finds all words made of letters, numbers, or underscores. It returns a list of words: user, Alice, ID, and 123. Finally, we use re.match to check if the string starts with the word user. Since it does, we print a confirmation message. This shows how the RE module helps match and extract patterns from strings. Let's look at some other pattern matching examples. The first example finds all digits in the string A3b. The pattern uses \d, which matches any digit from 0 to 9. The result is a list containing the number 3. The second example finds all word parts in the string user_1 is valid. \w with a plus sign matches sequences of letters, digits, or underscores. The result is a list: user_1 is and valid. The third example looks for white space characters in the string AB tab C newline D. \s matches spaces, tabs, and new lines. The result is a list with a space, a tab, and a new line. The next example finds all characters in the word cat. The dot matches any character except a new line. The result is a list with C, A, and T. The fifth example checks if the string starts with high. The caret symbol means start of string. Since the text begins with high, the result is a match. Let's look at some other examples. The first one checks if the string ends with end. The $sign means end of string. Since the sentence ends with end, the result is a match. The next example finds parts that start with L, followed by 0 or more O characters. It matches things like LO, LOO, and so on. In the phrase hello, Lou, loop, it finds LO, LOO, and LOO. The third one finds sequences of G, followed by one or more O characters. In the phrase, it finds GO, GOO, and GOOO. In the fourth one, we check for the word color with an optional U. That matches both color and color with U, but not color with W. So the result is a list with color and color. The final code finds any single character that is either A, B, or C. In the sentence apple, bat, cat, it matches multiple A, one B, and 1C. The next example finds any character that is not a digit. In the string A1, it returns the letter A. The second one looks for the exact sequence ABC as a group. In the string ABC123, it finds a match and captures the group ABC. The third example matches either A or B in the word bat. The result is a list with B and A. In number 4, the pattern looks for exactly 3 digits in a row. In the string, my code is 123456, it finds 123 and 456. And the final example finds numbers that are between 2 and 4 digits long. In the string year 2025, code 45, it finds 2025 and 45. Now let's look at some examples from pattern searching and replacing. The first code looks for a phone number in the format of 3 digits, a dash, 3 digits, another dash, and 4 digits. In the string call me at 123-456-7890, the search finds a match. The second code checks if there's a valid email address in the string. My email is name@example.com. It looks for a word, then an @ symbol, another word, a dot, and a domain. Since the format matches, it returns a match object. The third code replaces all numbers in the sentence, my code is 1234 and zip is 56789, with the word number. The result becomes, my code is number and zip is number. The fourth code finds sequences of 2 or more spaces and replaces them with a single space. In the string too many spaces with extra spacing, it cleans it up to just 1 space between words. The last code takes a date in the format year-month-day and turns it into day/month/year.
File formats and APIs. Working with JSON and XML.
In this section, we look at how Python works with 2 common data formats, JSON and XML. The JSON module is used to read and write JSON data. It's lightweight, easy to read, and commonly used in web APIs. For XML, Python provides the element tree module under xml.etree, which helps parse and navigate tag-based data. While JSON is more popular today, XML is still found in legacy systems, configuration files, and some APIs. Now let's see how to use both formats in code. First, we import the JSON module and create a dictionary. We convert it to a JSON string using json.dumps, and then back to a Python object using json.loads. Next, we define a simple XML string with user data. We parse it using elementtree.fromString, then extract values using the find method on the root element. This shows how to work with both JSON and XML in Python, converting data in and out of structured formats.
Making API requests using requests.
Python's requests library is the standard way to talk to web APIs. When we say make HTTP calls, we mean sending a request to a website or service and receiving data in return, usually in JSON format. The most common types of requests are GET and POST. GET is used to retrieve data from a server. POST is used to send new data to a server, like when you submit a form. When making these requests, we can send extra information. The params argument is used to pass query parameters in a GET request. These appear in the URL, like a name equals Alice. The headers argument is used to send metadata, like API keys or content type. The JSON argument is used in POST requests to send a Python dictionary as JSON data. The response we get back from the API includes useful information. Status code tells us if the request was successful. For example, 200 means OK. Text gives us the raw response body as a string. JSON converts the response body into a Python dictionary if it's JSON data. Let's look at a full example that uses all of these in action. First, we import the requests library. We send a GET request to the Agify API with a query parameter, name equals Alice. Agify.io is a simple web API that predicts the age of a person based on their first name. The params argument lets us pass query data. We print the status code to check if it succeeded. 200 means OK. Then we show the raw text response and parse the JSON with response.json. Next, we send a post request to httpbin.org, which is a testing service. We include some data using the JSON argument, a dictionary with a username and password. We print the status and the part of the JSON response that contains our posted data. This is a clean and simple way to interact with REST APIs in Python.
Testing. Unit test.
Python comes with a built-in testing framework called unit test. It allows you to write and organize automated tests to check if your code works as expected. To use it, you define a test class that inherits from unittest.testCase. Inside that class, you create methods that test your code. The method name should start with the word test, so unit test knows it's a test case. You use built-in assertions like assert equal, assert true, and others to check the expected output. Finally, calling unittest.main runs all your tests automatically when the file is executed. Here we define a simple function called add, which adds two numbers. Then we define a class named testMath that inherits from unittest.testCase. Inside it, we define three test methods. TestAddPositive checks if 2 plus 3 equals 5. TestAddNegative checks if -1 plus -1 equals -2. TestAddZero checks if 0 plus 0 equals 0. Each test uses self.assertEqual to compare the actual result to the expected value. Finally, if we run the script, unittest.main finds all test methods and runs them. If all tests pass, we'll see OK in the output.
Setup and teardown methods.
In unit test, the setup and teardown methods help you manage preparation and cleanup before and after each test runs. The setup method is automatically called before each test. You can use it to create objects, open connections, or set up any shared resources your test needs. The teardown method runs after each test and is used to clean up. For example, closing files or resetting states. These methods help you avoid writing the same setup code in every test, keeping your test classes clean and dry, meaning don't repeat yourself. In this example, we define a simple sample class that stores a list and can add or clear items. Inside the test class testSample, we define setup, which creates a new sample object before each test. Then we have a teardown method that clears the data after each test. The first test, TestAddOneItem, adds a single item and checks that the length is 1. The second test adds 2 items and verifies the list contents. Thanks to setup and teardown, each test runs in a clean environment with no leftover data from the others.
Mocking with unittest.mock.
In testing, mocking means replacing real parts of your code with fake ones, so you can control and test behavior without relying on real systems like databases or APIs. Python's unittest.mock module provides tools for this. The mock class can simulate the behavior of objects, functions, or methods. The patch function temporarily replaces real objects during the test, useful when you don't want to actually call an API or open a file. Mocking helps you isolate the code you're testing and avoid slow, flaky, or risky dependencies. In this example, we want to test the processData function. That function calls another one called getDataFromAPI, which is supposed to return some data from an external source, like a remote server or an API. But here's the problem. That function is not implemented yet. Even if it were, we wouldn't want to call a real external service during unit testing. So instead, we mock that function using patch from the unit test mock module. The @patch decorator temporarily replaces the getDataFromAPI function with a fake version, a mock object, only during the test. Inside the test method, we tell the mock to return the string hello whenever it's called. Now, when processData is executed, it doesn't call the real API. It just gets hello from the mock and turns it into uppercase. We then assert that the result is hello, which proves the function works correctly when given valid input. This approach lets us test the internal logic of processData without depending on unfinished code or unreliable external services. Mocking like this is a key part of writing clean and independent unit tests.
PyTest.
PyTest is a popular third-party testing framework that is simpler and more flexible than Python's built-in unit test. With PyTest, you don't need to define classes or use special assertion methods. You just write functions whose names start with test underscore and use regular Python assert statements to check your code. PyTest will automatically find and run all test functions in files that start with test underscore, like test_math.py. To run your tests, you just open a terminal and type PyTest. It will show you which tests passed or failed with clean and readable output. Let's look at an example that shows how simple PyTest can be. In this example, we define a function called add that simply returns the sum of two numbers. Below that, we define three test functions. Each function name starts with test underscore, which is required for PyTest to recognize it. Inside each test, we use a plain Python assert statement to check the result of calling the add function. For example, test add positive checks if 2 plus 3 equals 5. Test add 0 checks if 0 plus 0 equals 0. And test add negative checks if -1 plus -2 equals -3. To run the tests, you would open a terminal and type PyTest. The output shows that all three tests passed, using dots to represent success. Compared to unit test, PyTest is less code-heavy and easier to read, especially for small and fast tests.
Test-driven development, TDD, basics.
Test-driven development, or TDD, is a coding strategy where you write tests first before writing any actual code. The development cycle is often described as red, green, refactor. First, you write a test for something that doesn't exist yet. It fails. That's the red step. Next, you write just enough code to make the test pass. That's green. Finally, you improve or clean up the code. That's the refactor step. This process helps you think clearly about what your code should do, keeps your design simple and testable, and prevents bugs. You can use either PyTest or unit test to apply TDD in Python. Let's look at a basic example using PyTest. In this TDD example, we start by writing a test before any real code exists. The test checks if calling a function named greet with the name Alice returns hello Alice. But at this point, the greet function doesn't exist. So if we run this, it fails with a name error. That's the red stage. Next, we write just enough code to define the greet function so the test can pass. The function returns a formatted string saying, hello Alice. Now the test passes. This is the green stage. Lastly, we check if the code can be cleaned up or improved. That's the refactor step. In this case, the code is already clean. This simple cycle, red, green, refactor, helps keep code focused, well-tested, and easier to maintain.
Debugging and logging. PDB Debugger.
Python provides a built-in debugging tool called PDB, short for Python Debugger. To use it, you insert the line import PDB, pdb.set_trace, open and close parentheses, anywhere in your code. When Python hits that line, it pauses execution and lets you inspect what's going on at that moment. You can then step through the code, line by line, check variable values, and watch the program's flow. Some useful commands are N for next line, S to step into a function, C to continue running until the next breakpoint, P to print a variable, Q to quit the debugger. PDB is extremely helpful for tracking down tricky bugs interactively and understanding how your code executes in real time. In this code, we define a divide function that takes two values and returns the result of dividing A by B. The main function sets x to 10 and y to 0. Then we insert the line import PDB, pdb.setTrace, which starts the Python debugger at that exact spot. When we run the program, Python pauses right at the line print divide x, y. At this point, we're inside the debugger and can type commands to investigate what's going on. One common command is p, short for print. When we type px, we're telling the debugger to print the value of the variable x. This shows us that x is 10. Similarly, if we type py, it prints the value of y, which is 0. After that, if we type n, which means next, the program will try to run the current line. And since it's dividing by 0, we get a 0 division error. Using PDB like this lets us pause the program, examine values, and understand exactly why something goes wrong before it crashes. This is especially useful for debugging complex issues that aren't easy to spot by just reading the code.
More PDB commands.
Let's explore some more useful PDB commands to help you navigate and control code during debugging. First, use L, short for list, to display a few lines of source code around the current line. This helps you see what's happening nearby. To set a breakpoint, use B followed by a line number. For example, B12 sets a breakpoint at line 12. You can set multiple breakpoints, and when the program reaches one, it will pause. To remove all breakpoints, type CL, short for clear. Now, S stands for step into. It lets you go inside a function call line by line. Very useful if you want to see what happens inside another function. R means return. It tells the debugger to continue running until the current function returns, and then pause again. C, short for continue, resumes the program and only stops if it hits another breakpoint. And finally, Q is for quit. It exits the debugger and stops the program immediately. These commands give you full control to pause, inspect, and step through your code, which makes tracking down bugs much easier. In this example, we define an add function and a main function. Inside main, we pause the program using pdb.setTrace. When the debugger starts, we can use L to list the surrounding lines of code. Then, we might set a breakpoint with B7, which tells Python to stop again at line 7 if we continue. Next, using S for step into, we can dive inside the add function line by line. Inside it, we use px to print the value of the x parameter. Typing R continues until the current function finishes. This helps skip over internal lines if we don't need all the details. Then, we type C to continue execution normally, or Q to quit debugging if we're done. Mastering these commands helps you become a faster and more confident debugger in Python.
Logging module.
The logging module in Python is a built-in tool for tracking events while your program runs. Unlike print statements, which are temporary and hard to manage, logging gives you a structured, controllable, and professional way to monitor what your code is doing. Logging messages have different levels of importance. Debug is for detailed diagnostic information. Info is for general events that confirm the program is working as expected. Warning is for things that are not errors but could become problems. Error is for issues that prevent a part of the program from working. Critical means a serious error that may stop the program entirely. To start logging, you usually call basic config to set up the logging level and message format. Then you can call logging.debug, logging.info, and so on, depending on what you want to record. Logging is more powerful than print statements and is a best practice for real-world applications. In this example, we start by importing the logging module. Then we configure it using logging.basicconfig. We set the level to debug, which means it will capture all messages from debug level and above. We also define the format to show the timestamp, the level name, and the message. After that, we call different logging functions like debug, info, warning, error, and critical, each with a short message. When we run the code, the output includes the date and time, the level of each message, and the message itself. This system helps you monitor and diagnose your program without cluttering your code with print statements. And you can also write logs to a file instead of the console if needed.
Logging to files and custom loggers.
In real applications, you'll often want to save logs to a file instead of printing everything to the terminal. To do that, just add the file name parameter to logging.basicconfig. This tells Python to write logs to a file. For larger or modular applications, it's a good idea to use custom loggers. Instead of using the root logger, call logging.getLogger and pass a name, for example, the module name. You can then control each logger independently, such as setting its log level with setLevel, or adding handlers to send log messages to files, the screen, or both. This is especially useful in projects where you want to separate logs by component or only log detailed info from specific modules. Let's see an example that logs to both a file and the console using a custom logger. Here we create a custom logger using logging.getLogger and name it MyApp. We set its level to debug, which means it will catch all messages at debug level and above. Then we create two handlers. The first is a file handler, which writes logs to a file named app.log. We set its level to info, so it only logs info, warning, error, and critical. No debug messages go into the file. The second handler is a stream handler, which prints to the console. We set its level to debug, so it shows everything. We also create a formatter that defines how each log line should look, with time, logger name, level, and the message. We apply the formatter to both handlers. Finally, we attach both handlers to the logger using addHandler. Now, when we call logger.debug, it prints to the console only, but logger.info, warning, and error messages go to both the console and the log file.
Multithreading and multiprocessing. Threading and multiprocessing modules.
In Python, when we want to run multiple operations at the same time, we can use either the threading module or the multiprocessing module. Let's start with threading. It allows you to run multiple tasks within the same process, which means threads share memory and state. This makes it efficient for input-output bound tasks, like reading files or handling network operations. On the other hand, multiprocessing runs each task in a separate process. These processes don't share memory, so it avoids certain issues like the Global Interpreter Lock, or GIL. It's best for CPU-bound tasks, like data processing or mathematical computations. Both modules use a similar syntax. You create either a thread or a process, passing the target function to run. Let's look at a short example for both. We begin by importing both threading and multiprocessing, as well as the time module. The task function simply prints a starting message, waits for 2 seconds, and then prints a finished message. First, we create a thread object by calling threading.thread with the target argument set to our task function, and pass in the name thread using the args argument. We call start to run the thread, and join to wait for it to complete. Next, we do the same with multiprocessing. We create a process object with the same target and arguments. .start begins the new process, and join waits for it to finish. The output shows that the same function is run in both a thread and a process, but the difference lies in how they run. Threads share memory in a single process, while processes are fully isolated and use separate memory space. Knowing when to use which depends on the kind of task. Threads are best for waiting tasks like file or web access, while processes shine in number crunching or heavy computation.
Thread synchronization, lock and rlock.
When using threads, all of them share the same memory space. This makes communication between threads easy, but also dangerous, because if 2 threads modify the same data at the same time, we can get race conditions. To prevent this, we use a lock. A lock allows only one thread at a time to access a shared section of code. You call acquire before accessing shared data, and release after you're done. If a thread tries to acquire a lock that's already held, it will wait until it's released. There's also rlock, which stands for reentrant lock. It allows the same thread to acquire the lock multiple times, which is useful for nested function calls that all need locking. Let's see how to use lock and rlock in practice. In this example, we have a global variable named counter, and we want to safely increment it from multiple threads. We create a lock using threading.lock. Inside the safe increment function, we loop 1,000 times. For each increment, we first call lock.acquire before modifying the counter, and then lock.release to free the lock. This ensures only one thread at a time can increase the counter, preventing race conditions. We then start 5 threads, all running the safe increment function. Finally, we wait for all threads to finish using join and print the counter. Without the lock, the final count might be less than 5,000 due to race conditions. With the lock, we ensure every increment is safe and the result is correct. If we needed to acquire the same lock multiple times from the same thread, like in recursive calls, we would use threading.rlock instead.
Deadlocks and avoiding them.
A deadlock happens when 2 or more threads each hold a lock and wait indefinitely for the other lock. In that situation, none of the threads can proceed, and your program hangs. To prevent deadlocks, follow a few rules. First, if you ever need more than one lock, always acquire them in the same order in every thread. That way, threads won't end up waiting on each other in a cycle. Second, you can use lock.acquire timeout equals instead of a blocking acquire. If the lock isn't available within your timeout, You can release any locks you already hold and retry. Finally, sometimes it's simpler to use Python's higher-level synchronizers like rlock or semaphore, which can reduce the risk of deadlock in complex designs. In this first example, we're intentionally creating a deadlock to understand how it happens. We have two locks, called lock A and lock B. One thread runs task 1, which acquires lock A and then pauses briefly using sleep. After the pause, it tries to acquire lock B. At the same time, another thread runs task 2, which does the opposite. It first acquires lock B, then sleeps, then tries to acquire lock A. Now here's the problem. After both threads acquire their first locks, they each try to acquire the second lock, which is already held by the other thread. Neither of them can move forward, and both are stuck waiting forever. This is a classic deadlock, and it causes the program to hang. You won't see any output because the threads are blocked permanently. In this improved version, we solve the deadlock problem by making sure both threads acquire locks in the same order. We sort the two locks using the built-in ID function, which returns a unique identifier for each lock object. This means both threads will always acquire the lower numbered lock first and the higher one second, no matter what. As a result, one thread might wait, but it will never get stuck forever because no circular waiting occurs. This strategy, using a consistent global order when acquiring multiple locks, is one of the most important techniques to prevent deadlocks. In the output, we see both tasks complete successfully, and the program finishes without hanging. In this example, we avoid deadlock by adding timeouts when trying to acquire locks. The thread first tries to acquire lock A, and if it fails within 0.2 seconds, it prints a message and exits. If it does get lock A, it then tries to get lock B. If that fails, it prints a message and exits. But before that, it releases lock A to avoid blocking others. This retry pattern prevents threads from holding on to locks when they can't get what they need. Even if contention is high, threads back off instead of causing a deadlock. In the output, one thread completes fully and prints success. The other may fail to acquire the second lock and prints that it's backing off. This is a safer way to use locks when timing and responsiveness matter. In this example, we use an rlock, which stands for reentrant lock. A normal lock can only be acquired once by a thread. If the same thread tries to acquire it again without releasing it, the program will hang. That's another form of deadlock. But rlock is different. It allows the same thread to acquire the same lock multiple times, as long as it releases it the same number of times. This is useful in scenarios like nested function calls or recursive functions, where the same lock might need to be used multiple times in the call stack. In our example, a thread acquires the outer lock, then immediately acquires it again inside a nested block. The output shows that both lock acquisitions work correctly. This would fail with a regular lock, but succeeds with rlock. Finally, we use a semaphore to allow a limited number of threads into a critical section at the same time. We create a semaphore that allows up to 2 threads in. 4 threads are started, and they all try to use a shared resource, but only 2 can enter at once. The others have to wait until someone exits and releases the semaphore. This is useful when you have a limited pool of resources, like database connections or network sockets. It prevents overload and controls access without needing a separate lock per resource. In the output, you'll see only 2 threads running their task at once. As soon as one finishes, another thread takes its place.
Asynchronous programming, Asyncio.
Asyncio module is Python's built-in library for writing concurrent code that performs well with I/O-bound tasks like web requests, file operations, or network delays. First, we define asynchronous functions using the async def keyword. These are called coroutines. Inside those functions, we use the await keyword to pause and wait for another coroutine to complete without blocking other tasks. To run your asynchronous code, use asyncio.run, followed by the name of your top-level coroutine. Instead of using the regular time.sleep, we use asyncio.sleep to pause for a while without blocking the entire program. This model is different from multithreading. It uses a single thread and an event loop to switch between tasks that are waiting on something external, like a web response. That makes it highly efficient for applications like chat servers, web scrapers, and I/O-heavy automation. Let's look at the code to see how this works in practice. In this code, we import the Asyncio module. We define an asynchronous function called fetch_data using async def. Inside it, we print a message, then call await asyncio.sleep, which pauses the function for 2 seconds. This pause is non-blocking, so if there were other coroutines, they could run in the meantime. After the wait, it prints done fetching and returns some sample data. Then we define another coroutine called main. It prints main starts, then waits for the fetch data coroutine to complete using the await keyword. When the result comes back, it prints the data and ends. Finally, we start everything using asyncio.run with the main coroutine. In the output, you can see how tasks are executed in order, but the delay inside fetch data didn't freeze the program. It simply paused that one coroutine. This is the core benefit of Asyncio: efficient waiting.
Database interaction. SQLite with SQLite 3.
SQLite is a lightweight, file-based SQL database, perfect for development, testing, or small apps. Python comes with SQLite 3, so there's no need to install anything extra. First, use connect to open or create a database file. Then, create a cursor object using con.cursor. The cursor is used to execute SQL commands, like creating tables, inserting data, or querying records. After executing write operations, use con.commit to save changes to the file. When you're done, call con.close to safely close the connection. To read data from the database, use fetch1 to get a single row, or fetch all to get all matching rows. Let's walk through a simple example that creates a table, inserts some data, and reads it back. We start by importing the SQLite 3 module. Then we connect to a database file called example.db. If the file doesn't exist, it will be created automatically. Next, we create a cursor object. We use the cursor to execute a SQL command that creates a table named users, with columns for ID, name, and age. The ID is set as the primary key and will auto-increment. Then we insert one row into the table using question mark placeholders. This is called parameter substitution and helps avoid SQL injection. After inserting, we call commit to write changes to the file. Next, we query all records from the users table and store them in rows using fetch all. We loop through each row and print it. The output shows one row with ID 1, name Alice, and age 30. Finally, we close the connection using con.close. This pattern, connect, cursor, execute, commit, close, is the basic structure for working with SQLite in Python.
Basic SQL commands.
These commands form the backbone of interacting with any database, and they work the same in SQLite. First, we use createTable to define the structure of a new table, including the column names and data types. Then, insertInto is used to add new rows of data. To read data, use select. You can add a where clause to filter the rows, use order by to sort them, and limit to restrict how many results you get. If you need to change existing records, use update along with a where condition to target specific rows. Finally, to remove rows, use the delete command with a where clause. When writing these commands in Python, always use question mark placeholders instead of manually inserting values into strings. This keeps your code safe from SQL injection attacks. Also, remember to call commit after any insert, update, or delete. Otherwise, changes won't be saved. First, we connect to a database called people.db and get a cursor. We create a table called people with 3 columns, ID, name, and age. Then, we insert 2 people, Bob, age 25, and Carol, age 28. We use question mark placeholders to pass values safely. After inserting, we call commit to save the changes. We run a select star from people query to show all rows. It prints both entries. Then we update Bob's age to 26, commit again, and run another select to check. It confirms that Bob's age is now updated. Finally, we delete Carol's record using her name, commit again, and check all rows. The final output shows only Bob remaining. This flow shows the core SQL commands: create, insert, select, update, and delete, all used inside Python using the SQLite 3 module.
ORM basics like SQLAlchemy.
In this page, we'll introduce ORM, which stands for Object Relational Mapping. An ORM lets you work with databases using Python classes instead of raw SQL statements. One of the most popular ORMs in Python is SQLAlchemy. It allows you to define tables as Python classes and rows as objects. You can insert, query, update, and delete records using regular Python code. With ORM, you don't have to write SQL directly. SQLAlchemy handles the translation behind the scenes. To start, you define your model classes using Python. Each attribute becomes a column in the database table. Then you create a session object to talk to the database. This is how you insert, fetch, or change rows. This method improves readability, reduces errors, and makes your code more maintainable, especially in larger projects. In this code, we use SQLAlchemy to build and use an object-oriented database model. First, we import the necessary parts, including create engine, column, integer, and string, and the ORM components like declarative base and session maker. We create an engine that connects to a SQLite database file named orm_example.db. We define a base class called base using declarative base. All our models will inherit from this. We define a class called user that maps to the user's table. Each class attribute becomes a column: ID, name, and age. We then use base.metadata.createAll to generate the actual table in the database. Next, we set up a session using Session Maker. A session lets us interact with the database. We create a new user object named Diana and add it to the session. When we call commit, the record is inserted into the table. Then, we query all users from the database and print their names and ages. The result shows that Diana, age 34, is stored. This is a basic ORM flow. Define models. Create a session, add objects, commit, and query, all in clean, readable Python.
GUI development. Tkinter.
In this page, we'll introduce Tkinter, the standard GUI or graphical user interface toolkit included with Python. Tkinter allows you to create graphical user interfaces like windows, buttons, text boxes, and more using simple Python code. You begin by creating a main window using TK. This initializes the graphical interface. Then you can add widgets, which are UI components like label, button, and entry. To place them in the window, you can use pack, grid, or place methods. Finally, call main loop to display the window and start the event loop. This keeps the window open and responsive to user interaction. Let's look at a simple GUI with a label and a button. Let's walk through how to build a very simple GUI using Tkinter, step by step. Step 1. We start by importing the Tkinter module. We rename it as TK to make our code shorter and easier to read. Step 2. We create the main application window. We do this by calling tk.tk. This creates the root window where all widgets will live. We also set a title for the window using root.title. Step 3. We create a label widget. A label is used to display static text. We write tk_label and pass it two arguments, the parent window, which is root, and the text we want to display. In this case, hello Tkinter. We then call pack on the label. Pack is one of the layout managers. It automatically places the widget in the window. Step 4. We define a function called onClick. This function is what we want to run when the button is clicked. Inside this function, we change the text on the label using label.config and pass a new text value. Step 5. We create a button widget using tk.button. Again, we pass the parent, which is root, and the text for the button. But this time we also pass command equals onClick, so that our function is run when the button is pressed. We pack the button into the window using .pack again. Final step, we call root.mainLoop. This tells Tkinter to start running the GUI. This line keeps the window open and makes it interactive. So to summarize, you start with tk.tk for the window. Create widgets like label and button. Use pack to place them, and use main loop to launch the interface. This structure forms the base of almost every Tkinter app you will build.
Entry fields and layouts in Tkinter.
Now let's go deeper into entry widgets for user input and how to use the grid layout system in Tkinter. First, let's talk about the entry widget. This is used to create a single-line text input, similar to an input field in a form. To read the text from an entry, we use the get method. To insert text programmatically, we use insert. Next, instead of using pack to position our widgets, we can use grid. Grid lets you place widgets in a structured layout using rows and columns. Think of grid like a table. Each cell has a row and column number. For example, labels can go in the first column and entries in the second. This makes it easy to create form-style layouts. One important rule: don't mix pack and grid in the same container. It may crash or behave unpredictably. Let's see an example that uses label, entry, and button in a structured grid layout. Let's walk through how to create a simple form layout in Tkinter using entry widgets and the grid layout manager. Step 1. We import Tkinter as TK, then create the main window using tk.tk and give it a title. Step 2, we create two label widgets, one that says name and one that says age. We use the grid method to position them. The name label is placed in row 0, column 0. The age label is in row 1, column 0. Step 3. We add two entry widgets. The first entry is stored in the variable name entry and placed in row 0, column 1. The second entry goes in row 1, column 1. Now we have a two-row form with labels on the left and text fields on the right. Step 4. We define a function called submit. Inside it, we call .get on both entry widgets to read the user's input. We print the name and age to the console. Step 5. We create a button labeled submit. The command is set to the submit function so it runs when clicked. We place it in row 2 and set column span equals 2 so the button stretches across both columns. Finally, we call main loop to start the interface. When the app runs, you get two labeled text fields and a button. Enter a name and age, click Submit, and the data is printed in the terminal. This layout is clean, structured, and easy to scale for more form fields.
Introducing PyQt, or Kivy, for advanced GUI.
When your GUI application needs to go beyond the basics, two powerful frameworks come into play: PyQt, or PyQt, and Kivy. Let's start with PyQt. PyQt provides Python bindings for the Qt toolkit, a professional-grade C++ library. It's ideal for building desktop applications that look and behave like native apps on all major platforms. PyQt applications are built using widgets, and they rely on a system of signals and slots for event handling. For example, when a button is clicked, it emits a signal, and you can connect it to a function called a slot. PyQt also comes with a powerful GUI designer and supports complex layouts, custom widgets, menus, dialogues, and more. On the other hand, Kivy is designed for cross-platform development, including mobile devices. It's touch-friendly and can run on Windows, Linux, Mac, Android, and iOS. Kivy supports building the interface using either Python code or a separate Kivy language, which is a simple markup format. Kivy is great for modern, dynamic, or multi-touch apps, like mobile utilities or games. So, in summary, use PyQt for powerful desktop apps with native controls, and choose Kivy when you want a modern, mobile-friendly interface.
Thanks for watching.